All right, so we're going to be down here. I changed things a little bit before class, just to kind of, I don't know, hopefully be a little bit clearer. So we're getting topics that cover, like, or kind of go over multiple weeks. So what we did a little bit last week and the week before was we kind of focused on these nonlinear regressions, adding in kind of squared terms, looking at logarithmic, log linear, et cetera. We then kind of transitioned last week into talking about interaction terms. We'll kind of pick up there this week. I'm guessing we probably won't get through all the material today. So mainly this week, we'll probably just talk about interaction terms. I'll just show you more examples along the way, sprinkle in some of this like log linear and linear log stuff. And then we'll kind of start in the next topic next week. I might introduce it a little bit on Thursday, but for now, we're just going to kind of live in where we started last class, which is this interaction term topic. Okay. So we're going to keep using that same do file. I've got the same kind of set of slides. I believe where we left off, it's coming down here. So we're talking about differences in slope. Before we dive into it, just a couple things to mention. That third problem set is third. The fourth problem set is due at the end of the day tomorrow, right? It was originally today. I then said I didn't have office hours yesterday. So if you have some last minute questions, I'll have office hours tomorrow. I might have some B251 students there, so the earlier you get there, probably the better. If you have any last minute questions, you can always email me. And if you don't want to stop by, I'll be around tomorrow early. So if you get there a little bit before 9:30 tomorrow, kind of beat the rush of the B251 students. I'll also be there a little bit after 12:30 if you want to kind of stop out between 12:30 and 1, just to kind of avoid that rush. I'll let you guys know about that. Okay. Any questions for me before we kind of dive back into material where we left off? Okay. So what we started doing was thinking about interacting dummy variables with dummy variables. And then we kind of moved on to thinking about interacting dummy variables with continuous variables. Right? So what we covered last class was thinking about, let's say I've got some y variable. I'm trying to predict it. And I'll kind of try to use this as like a dummy variable. And then I've got a continuous variable. Okay. And then I'm going to include an interaction of the two. So I think we looked at like some basketball shot data. We thought about like beauty and wages, and if that's treated differently for males versus females. Why is this thing not moving for me? There we go. So I think last class, really what we were looking at is what is the marginal effect of our continuous variable, right? So we have two groups, and by including this interaction term, right, we're multiplying the continuous by the dummy. We said if I were to take a derivative of this function in respect to that thing that I'm jumping the gun. In respect to that continuous variable, right? So what we'd be left with is our estimate for beta 2, right, with our continuous variable. And then the estimate of beta 3, well, if I take a derivative here, I'm still left with that dummy variable, right? So my marginal effect of the continuous variable, so it's like the marginal effect of beauty across males and females, or this looks variable. Really, we're going to have two different marginal effects, one for the 0 group and one for the 1 group, right? The marginal effect for the 0 group, well, this dummy variable will be 0. So our marginal effect there is simply the coefficient on that continuous variable. For the 1 group, we're going to have that coefficient on the continuous variable, but now this becomes a 1. So what gets added in? Beta 3 times 1. So we have this difference in the marginal effect. This continuous variable is going to have different impacts on y for these different groups. Okay? So when we were plotting this out, we said you can think about this almost as, let's just assume for a second that beta 1, the estimate we get, is 0. What that would mean is, what is the predicted starting point for our 0 and 1 group? Well, usually for the 0 group, it would simply be that constant. Now, if this wasn't 0, we would then have added in whatever that coefficient was on the dummy variable. But it could be that they start off at the same point if beta 1, right? Usually we would add beta 1 in here to get our second group. But if this is 0, both groups start out at the same point. So if we fail to reject the null for just that dummy variable, it's like our lines of best fit between this continuous variable and our y variable start at the same point. Usually that's not the case, right? Usually there's some significance on it, and so we kind of start out at a different point. But I just want to kind of do one where we're assuming there's no effect from belonging to this group, right? However, the effect of belonging to this group will change the marginal effect of our continuous variable. So now I'm using this continuous variable for group one, for a group that has the 0, right? Group 1, that's kind of confusing. For the group that has the 0 for the dummy variable, we said the slope, or this line of best fit, is only increasing by beta 2. Okay? So think about two scenarios. If beta 3 is in fact positive, that means the marginal effect for the one group, so you can think about here, this is for the group where the dummy variable is equal to 0. For the group where that dummy variable is equal to 1, we now get added in this additional coefficient. So the marginal effect, or that line of best fit, when that dummy variable is equal to 1, for that group, a 1 unit change in our continuous variable would actually increase the predicted y by beta 2 plus beta 3. Okay? So what we were doing with this interaction term is we're allowing the marginal effect of the continuous variable to be different for these two groups. Now, just so I'm not putting these on the same graph, right? We could think about a similar scenario. I'm going to start out. Let's say we had the same starting point. So we had find beta 1 here is 0. For my 0 group, that marginal effect is still just beta 2, right? Between this continuous variable and my y variable. What if, let's see, I don't know what color shows up the best. We'll try blue. What if instead the estimate for beta 3 is in fact 0? We actually end up with plenty of different combinations. So I could think about one is that it has the same starting point, but if this is negative, the marginal effect for the group where that dummy variable is equal to 1, it's still beta 2 plus beta 3 now. But if beta 3 is negative, the slope for that one group is going to be flat or not as large. So depending on the sign of our interaction coefficient, our kind of line of best fit for that group 1, or the group where the dummy variable is equal to 1, could be flatter or steeper. Is this hopefully looking a little bit familiar? Kind of, I know we're not putting specific variables here. We'll kind of jump into state and look at this here in a second. Any questions on this idea? Now, the way that I've drawn this, the marginal effect is still positive for both groups, right? It's just larger for one versus the other. What could be the case is if you think about, what if this negative effect, what if beta 3 was larger than beta 2? What's that going to look like in terms of our line of best fit? Well, got my continuous variable, my y variable. Maybe here's the 0 group, right? And I had this positive coefficient for beta 2. If beta 3 is negative, and in fact, it's such a large negative value, it's greater than beta 2, what's going to happen to my slope? If I take beta 2 plus beta 3 is a larger negative value, my slope is now going to be negative for that one group. So we can identify differences in the marginal effect between these two groups. It doesn't necessarily mean the effect is always positive for both groups. In fact, if that interaction term coefficient, estimated coefficient, is large enough, you could actually see the marginal effect for the two groups is a completely different sign. Okay? Any questions on this before we keep going? This is kind of where we left off. We're just kind of revisiting. Okay. So what we didn't quite talk about is, what if I wanted not the marginal effect of my continuous variable, but what if I wanted the marginal effect? So we'll start out kind of with this same equation. Okay. What if instead, now I'm interested in the marginal effect of my dummy variable? So if I'm doing that, I'm going to have a difference in the marginal effect for the group that has a 0 and the group that's identified with a 1. So if I was taking a derivative of my linear regression function in respect to that dummy variable, what am I left with? Well, I would have beta 1, but now plus beta 3 times that continuous variable. Now, if I have the 0 group, right, what would my marginal effect actually be? Right? So this is going to be the marginal effect of being in that group. So what's the marginal effect of not being in that group? It's always, if I have zeros here, what's the marginal effect of being in the 0 group? Nothing. That's my basis, right? That's my starting point. All right. So here, there really is, if I'm in group 0, there is no marginal effect of the dummy variable, right? It's equal to 0 for me. So what we're really thinking about is how does the marginal effect of that dummy variable vary for group 1? Okay. Well, the problem is it now has kind of this starting point, right? Where we kind of shift my line of best fit. But it will also shift that line of best fit differently for different values of that continuous variable. So I could now think about if I was doing, I think I'll do one here in a second where it's like the effect of the officer, or what did I want here? I think I had the officer being male and then kind of their years of service or something like that. So the marginal effect of being a male officer will vary depending on how long I've been in service. Right? So now the marginal effect of my dummy variable depends on what I interacted it with, which is that continuous variable. So we can look at the marginal effect of the continuous variable. That's what we did last class. Allows for difference in the slopes between these two groups. The marginal effect of the dummy variable, well, there is no marginal effect for group 0 because the dummy variable is equal to 0. But the marginal effect for group 1, it's now not just going to be simply kind of moving that group's coefficient or that starting point. It's going to move the starting point differently for different values of that continuous variable. Okay? So we can now think about if I've got a marginal effect of this dummy variable, and it's equal to this, right? And here I'll just write that's continuous variable. When will this be equal to 0? Right? Well, if I rearrange this equation a little bit, what continuous value, what value for that continuous variable will I get a marginal effect equal to 0? If I just rearrange this a little bit, I end up with what? So I move this over. Something like that. If I just do the algebra, I subtract this from the side, divide by negative beta 3, I end up with, I'm now going to have, kind of similar to when we had that squared term, I'm going to have a turning point, right, for that marginal effect, right? Maybe, right? So why is the answer maybe here? So we have different combinations that we could see. If beta 1 is positive and beta 3 is positive, a positive over positive times a negative, my turning point would actually be a negative value. If I was using my example for like the officer's years of service as a continuous variable, can I ever see a negative turning point? No. So this is where we can calculate a turning point, but sometimes a negative value wouldn't make any sense for the variable of officer's years of service. Now, if we were looking at the continuous variable of something like, I don't know, firm's profits, right, or returns on investment, well, there we could see positive, negative values, so maybe that turning point makes sense. Similar kind of idea. What if both of these were negative? Well, in both scenarios, I'm going to have a turning point that's negative. Maybe that makes sense if I've got a variable that's like returns, but for officer's years of service, it wouldn't make any sense at all, right? So I can always identify the turning point. It's just that sometimes it won't make sense that it exists in the data. Now, for almost all variables, right, we have some positive values, and probably what's more common is if I have any I have the other two, combinations. So something like this. Is this on the screen? Just barely, okay? So if I have different signs, well, a negative over a positive times a negative is positive. Positive over a negative times a negative is positive. So here, I'd end up with a turning point that's positive. So in my example, like officers' years of service, this point actually likely exists in the data. So we can calculate what that turning point is for the marginal effect of that dummy variable. Sometimes it will exist in the data, sometimes it won't. Okay? So we'll kind of work through some examples to kind of get a taste of this. But here we're looking at the marginal effect of our dummy variable. Right? So any questions on this before we keep moving? Okay. So what do I want to do here? Switch down here. So maybe here, I want to know the marginal effect of being female. So we had that kind of example we looked at last class. We're running our Y variable is wages, our dummy variable is being female, our continuous variable is looks. If I want to know the marginal effect of being female, well, I've got the effect here, right? But I also have an effect that comes from the interaction term with looks. I basically would use those coefficients. In my example earlier, that was beta 1 and beta 3. I could then calculate that marginal effect. Okay. Here was kind of a slide. I'm just looking at kind of my turning point. So we said that's going to be beta 1 plus beta 3 times whatever that continuous variable x is. If I go back to my regression output, beta 1 is always going to be that coefficient simply on the dummy variable. So for us, that's what, negative 0.53. The coefficient on the interaction term is 0.046. So we're basically using those two values. If I rearrange this equation, that value for that looks variable that represents the turning point, well, I have a negative sign out here. So when I move things over, we always had negative times beta 1 over beta 3, or negative 0.31 over 0.046. Okay. If I want to be a little bit more technical here, I kind of skipped a step. Right, there's a negative sign out front there, which is why I just kind of made it positive. Okay, but if you want a little bit more exact kind of what's going on, I skip some of the algebra here. That's what we'd have. Okay, so if I have this looks variable and I forget exactly what kind of the range was, but let's say it goes from like 0 to 100, is there a turning point that actually exists? Yes, right. This value for 11.5 would be somewhere in that range of that looks variable. Okay, is that any questions on this idea before we keep moving here? So this is where I want to get us some practice. Oh, and I forgot to add this. So let's go ahead and add this real quick. I have it sitting here, ready to go. Kind of come down here. I'll remind myself of the code I use. So we've got what? Some old quiz that I'm reusing. So let's look at today is the 31st. And we got what? We'll spend some time on this here. I'll kind of have you guys help me kind of reason through some of this, right? So we've got the next 17 minutes to get this done. And I'm going to go to build just to remind myself what that code is. So 10.09 is the number for the day. Okay. So that should get us kind of into that quiz. I don't know if I published it yet. So let's make sure I did. Oh, there we go. So 10.09 will get us into this quiz. We'll kind of start taking a look at it. Okay. So I'll go here. So I won't show you these, but we'll kind of work through these together. Just go to preview here so we can't see the answers. Okay. It's loading. It's loading. All right. So I had this data set that was looking at like married individuals, I believe, what their height was, and then what their mate's height was, or who their spouse height was. So here I didn't have any additional controls, right? Just a very basic regression where I've got a continuous variable, which is the individual's, spouse's height, and I have kind of whether or not their spouse was male or not. Okay? So I've got a dummy variable and a continuous variable, right? So if I come down here, I can kind of see when I use this hashtag, which said I could create the variable myself, or I've got the height variables coefficient, the male variables coefficient, and then the interactions coefficient. Okay. So looking at this output, if I was plotting the predicted mate height, which was my Y variable, if I was doing that for different levels of the spouses, their own height, for males, what would kind of be true? Okay. So I'm going to use these values. I'm going to plot this out, and then we can kind of reason through, I guess, sorry, which one's not true. Okay. So looking at these results, I'm just going to write this down. Well, we'll switch over. I'll write these down for you. So what was it? So the coefficient on my male variable is what? 10.99. The coefficient on that height variable of the spouse was 0.671 for rounding to the third decimal. And then that coefficient on the interaction term is what? Negative 2.8. If I round to the third decimal, we'll kind of round to 2.8 there. So let's kind of think about, also I've got the constant or the intercept. We'll kind of pull that with us as well and think about plotting what this looks like. So 27.71. So if I'm interested in this relationship, right, between an individual's own height and what the height of their spouse was. This is our y variable. This is our kind of continuous x variable. So I was thinking about, I kind of have the spouse or the mate height, and I was trying to predict this using whether or not their spouse was male, what their own height, or sorry, whether or not they were male, what their height was, and then an interaction between those two. Okay. So here I'm thinking about where's the differences in the starting point. So if I've got this group, this dummy variable, and it's 0 if they're female, 1 if they're male. So if the individual is female, what's the starting point for my line of best fit? Well, if they're female, this is equal to 0. This would be equal to 0. But here, the starting point is when height is also equal to 0. So for my 0 group, that intercept coefficient, or beta 0, is where it starts out. Okay. Now, if I think about what is the predicted change in mate height for that 0 group, or essentially, what is the marginal effect of the continuous variable, their own height, for females, right? Or this is where male is equal to 0. So if their own height goes up by 1, what would get added into my prediction? Beta 2. But if they're female, their own height multiplied by 0 would be 0. So for females, the only effect that's coming from height would be beta 2, which was what? The coefficient on height, so 0.671. So if we're thinking about kind of that predicted y variable, or the predicted mate height, that change is going to be simply beta 2, or simply that coefficient associated with that continuous variable. Now, what about for the other group? All right, so if I've got males, if their height is 0, where would their predicted mate's height start out at? The intercept. But now here, I would add in the coefficient associated with being male, right? So their starting point is going to be beta 0 plus beta 1. Beta 1 is that coefficient on male. What do we notice? It's positive. So it'd be what? Before we were down here at 27.71. Now we're going to be up here at what? 27.71 plus 10.99. So roughly what? 11. So 38.7. Or essentially, we're at a higher point. We're at a higher starting point. Any questions on anything up to this point? So we're just kind of plotting out what these coefficients are telling us. Okay. So you could then think about, all right, what is the marginal effect of this continuous variable for males? Okay. Well, if they're males, height goes up here by 1 unit. It would still increase my predicted mate's height by beta 2. But now if they're male, when height goes up by 1 unit, what also gets added into my prediction? Beta 3. Right? So that marginal effect of height, or our continuous variable, not for females, but for males, so that was where the male variable would be equal to 1, is now going to be beta 2, or that coefficient on height, but also the coefficient on the interaction term. Right? Because if I take a derivative here, I'm still left with male, but male is now 1, so beta 3 gets added in. Oh, yep, thank you. There we go. So what is the value of beta 3? Or what is the value on my interaction term? It's actually negative. So here, I'd have what? 0.671. That was the coefficient on height. I then have the coefficient on my interaction term. I'm getting roughly here, what, 0.4? I'm doing some egregious rounding. All right, this is going to be approximately 0.4. So the slope for males is actually flat, right? It's a smaller positive value than it was for females, because beta 2 here was 0.67. We just said the marginal effect for males here, and we're looking at their predicted mate height. So this was for males, is going to be beta 2 plus beta 3, right? Beta 3 was negative, so it's going to be a little bit flat. Okay. Any questions on this idea before we keep moving? Okay. So I don't know, what are the kind of options we have here? So for males, we said the effect of their own height is going to be flat. That's what we just said, right? The intercept for mate height is greater for females. Well, no, that's actually where we said the male's kind of starting point was a little bit higher, right? And then for females, the slope is going to be flatter. No, we actually said that was going to be steeper. So this should be the one that's not true. Let's check this one. Hopefully we're right. For females, the intercept is lower, or on mate height is lower than the intercept for, that one doesn't even make sense, right? I threw an answer here. We're always comparing the 0 to the 1 group, right? So here would always be comparing males to females. This final answer doesn't even make sense for us. So we can start to think about calculating these marginal effects, thinking about these lines of best fit. We're now allowing them to vary not only in their starting point, but then also that line of best fit to have a different slope for those two groups. Okay. Questions on that one before we keep moving? Okay. So let's run with the same example, right? And I run the following regression, get the exact same results. Okay. If I'm looking for the turning point for the marginal effect of being male, what is that going to be? Okay. So we're going to switch back over and say, okay, I've got these coefficients. Okay? If this is the regression equation I'm running, what is the change in my y variable, or my mate's height, divided by a change in that dummy variable, which for us was male? Well, if I take a derivative of this function, it's always going to be the coefficient on my dummy variable. Now, if they're male, I would also get added in that coefficient on the interaction term times the value of that continuous variable. So here I've got what? The male coefficient was what? 10.99. The interaction term coefficient was negative 0.28. So they're of different signs. So I'm going to end up with a turning point that's positive. Right? Well, that's good. That means the turning point actually exists because height can't be negative. I shouldn't say it's good, but at least we can have a turning point that has an actual purpose. So if I just rearrange this equation a little bit, when is that marginal effect equal to 0, or when does that turning point occur? Well, I'd have 10.99 minus 0.28 times the individual's own height. If I just rearrange this equation a little bit, I add this to both sides, I'd have what? 0.28 times height. I'll be mundane doing the algebra here. Divide both sides by 0.28. All right, whatever this works out to be, it's going to be what? Something roughly like 40 to 50, now somewhere in that range. We can plug in your calculator, figure out exactly where it's at, right? But it's going to be that coefficient on the dummy variable divided by the coefficient of our interaction term, but then there also should be a negative sign up front. That's just if we didn't plug in the values, that would always be what we get for the turning point. So for us, if we take 10.99 and divide it by 0.28, anybody want to help me with the math? Or I can pull up an Excel here to be our calculator. Unless anyone can beat me to it. We get what, 39.25? Okay. So if we're thinking about what is that turning point, should be, I already forgot what we found, 39.25. Okay. So as long as you're following along with me here, these shouldn't be too bad. Okay. Now, I want to make a point here. So that turning point exists. Okay. It's positive. People have to have a positive, I think this was inches, so they have to be some positive amount for height. But does this make sense? I mean, how tall would somebody be if they were 40 inches? What? Under 3.5 feet. So I don't know, the shortest person in the world, I think, is below 3.5 feet. But for most data sets, we're probably not going to see someone exist in the data set that's that short, right? And so there, would the marginal effect of being male on kind of mate height ever be kind of negative? Well, likely not, right? It's likely we'd ever see someone that was that, had that value for that turning point. If it was something more like, I don't know, 60 inches or something like that, well, then we start to see people who are 5 foot tall in our data set, and maybe that's where the marginal effect goes from being negative to positive. Okay. So for the sake of time, we have one more question we'll kind of work through, but just submit this quiz for the first 2 problems, and I'll kind of adjust it once I get back to my office. As long as you got those correct answers for the first 2, you'll get kind of the full points for today. Okay. So we just kind of worked through this one, found that turning point of 39.25. We said the only one that wasn't true up here was that the female slope is flat. Okay. I'm clear on that before we keep moving. Okay, so make sure I think I set it to be what, 120. So submit it here the next 2 minutes to make sure you're kind of getting full credit. We'll talk through 3, but I don't think we'll get quite through it before 120. So that's why we kind of just said submit it now. Okay. And don't worry about answering question 3. Like I said, as long as you answer the first 2 correctly, you'll get full points for the day. Any questions over anything we've talked about up to this point? Okay. So maybe something a little bit harder, right? If I was looking at this output, what is the predicted mate height for male who's 69 inches, right? So if I wanted to make predictions, I still use these coefficients, but I'm now not looking at the marginal effect. I'm looking at the total predicted value for that Y variable. So I kind of have these coefficients written down. It's the same thing here. Now, we're using this regression results. One thing that's kind of interesting here, now it's not the total marginal effect, but notice, is there a difference at a statistically significant level of the starting mate height for males and females? Well, if the continuous variable is equal to 0, here that coefficient on the dummy variable is actually not statistically significant. So we can't actually say that that starting point for the line of best fit is actually any different between these 2 groups. All right, we're really not sure. I mean, we should say we're not sure. We can say that at the 90% level, not quite. We failed to reject that that's anything different from 0. Okay, I was kind of treating it as though it was statistically significant, but if you were looking at these results and like, oh, it's not quite, you're right. We really should have been treating that coefficient on male as being equal to 0, right? But that's not as interesting of an example, so that's why I kind of ignored that for a second, okay? Now, if I wanted to come up with predicted mate height, if I've got this regression result, right, really all I'm doing is it's just like we were doing before with predictions, okay? So if I wanted to know that predicted value or mate height, right, what I would do is say, okay, include that coefficient estimate for the intercept, include the estimated coefficient for their male times male, estimated coefficient for their own height times height, and then also add in that coefficient on the interaction term, but then multiplied by both variables. So if I had a male who is 69 inches tall, I think that's the values that I used. All I would do here is say, okay, this value was what? 27.71. I would then have the coefficient on male, which was 10.99. This variable would be equal to 1, so that gets added into my prediction. I would then have the coefficient on height, 0.671 times their value for height, which we said was 69 inches. Now, when it comes to the interaction term, there we need to plug in our values as well. It's just we gotta be a little bit careful when we're making the predictions, because before we we're just plugging in the coefficient, multiplying it by the value of that variable. Now we've got the coefficient, but we need to multiply it by the value of each variable. This might seem kind of dumb at this point because dummy variables can only be zeros or one, so it either gets added in or it doesn't. We're going to move next to thinking about interactions between continuous variables, like multiple continuous variables, where it does matter. We're plugging in the values for each one of these. Okay, so this would be my predicted mate height for a male who's 69 inches tall. Any questions on anything here? So once again, this should be a little more simplistic. Like we're going back to just thinking about making predictions. We're not talking about marginal effects. We're just making predicted values here. Any questions on this idea? So I don't know. Maybe this is interesting. Maybe it's not. I thought this was kind of an interesting example that, like, for males, right? But actually, initially, so looks like there's a higher kind of starting point for their mate height. Problem is, when I'm thinking about the actual predicted mate's height, I forget where this exists. It exists pretty quickly, right? So as males get taller, yes, their mate's height is getting larger, but not as large as if a female is 1 inch taller. So this is probably somewhat stereotypical, right? A male going from like 70 to 71 inches doesn't have as large an impact on their mate's height as if a female is going from 70 to 71 inches, right? My wife's like my height, so I guess she goes against this a little bit. But this would be kind of how we're picking up differences in those marginal effects and those predicted values for Y. Okay. Any questions on this before we keep? So introduce this idea a little bit more in depth here today. It gets more complicated, right? So this is I'm not saying that this is easy, right? But we're going to kind of overcomplicate it a little bit, or not overcomplicate. We're just going to make it a little more complicated for different types of interaction terms. Okay. So let's look at how we do this in Stata. Right? So before we move on to continuous interactions, I think last class, we were going here. We had this traffic stop data. So I'm going to reopen that. We had a bunch of variables that we created. I'm going to do this here. So that should create a bunch of variables that we need. I'm going to again go down here and think about a slightly different regression based off what we talked about today. So here was kind of my original regression, right, under that interaction term heading. Okay. So we're going to look at a slightly different one here today. So I can include all of these additional controls, right? I'm going to do something here, though, where let's look at the interaction between the officer being male and officer's years of service. Right? So we've got a dummy variable and a continuous variable. I'm going to create where did I have this? This was officer's years of service was kind of the shorthand. So I'm going to create the interaction term. You can use that hashtag method. It's just, I don't know, it can get confusing about how you grab the coefficients from the regression results. I think here it's maybe a little bit easier as we kind of initially start looking at it. So all this variable is going to be is whether or not the officer was male times the officer's years of service. All right. So I'm going to create this interaction term. And then down here, I'm going to just rearrange things so that we can kind of have all of these at the very top. So I'm going to take officer being male. I'm going to delete that real quick. Officer's years of service. I'm going to delete that real quick and just put these at the front and also include my interaction. Whoops. my interaction term. It's just the way I'm kind of having them in the same place when we look at the results. It's not jumping back and forth. So if I'm looking at running this regression, so I'm going to create this interaction term. Hopefully everything's running smoothly here. Oh, what did I do differently here? Oh, I must have already created this variable. So now we're just going to run this regression. What did I miss here? I hit space on accident. I need a space down here. Right? Wait, what did I do wrong here? I copied something that I didn't want. What did I copy? Officer being white. Oh. I don't know why I added that in. We already have is the driver white. So we get rid of this. What's I add here? Oh, because I got rid of this. Hold on. Well, this is what we want, right? So we've got the officer being male, their years of service, the interaction, whether the driver was white, whether the officer was white, the driver was male, driver's age, and then the reason for the stop. Okay. So we run this regression, right? This is where I don't remember all these reasons, but we're controlling for the reason of the stop. We've got all these additional controls. We've got the continuous dummy variable and the interaction term we're interested in. Now, we don't have a lot of statistical significance here, right? In fact, the interaction term here, I can't say it's any different from 0, but we'll just act like it is statistically significant so that we can use these coefficients to think about marginal effects, okay? So if I'm thinking here, okay, let's say I wanted to know the marginal effect of the officer being male, okay? Well, if I know the marginal effect of the officer being male, I could also come up with oh, we'll just stick here for a second. All right. Marginal effect of the officer being male, okay? If I'm looking at if it's the officer male, what would get added into my prediction? Or essentially, what's the marginal effect of the officer being male? Well, it would be the coefficient on is the officer male. So here, if I'm kind of rounding that 4th decimal. But then also, I would be taking kind of a derivative of this function with respect to officer being male here. So it would be 1 times the officer's years of service and whatever coefficient is associated with that interaction term. So I would be adding in what? 0.0009, but then still multiplied by, right? This is my interaction term. When I take a derivative in respect to the officer being male, I'm still left with the officer's years of service, right? So this is like the total marginal effect of my dummy variable, right? This is, we went back to when I was writing out in general terms, the coefficient on the dummy variable plus the coefficient on the interaction term times that continuous variable. This is where we could actually solve for a turning point, okay? So here, if I'm looking at kind of this, I could have, I can't really use this display command because it's going to treat officer years of service as basically just a 1. But I know that can vary, right? So what I actually want to do is I'd want to make different predictions for what that marginal effect is based off of the officer's years of service, right? So I could make these marginal effect predictions, but it's going to vary with the officer's years of service. So what I'd actually want to do is something like, okay, what's the marginal effect if the officer has been working for 10 years? What is the marginal effect of the officer being male if they've been on the job for 20 years, right? I could then find what the marginal effect of the officer being male is for different values of that years of service, okay? Now here, both of these are positive. So what did we say the turning point was? Okay. So the turning point for the marginal effect of the dummy variable was going to be the dummy coefficient divided by the interaction coefficient, but I left something out here. What was out front? A negative sign, right? So if I'm thinking about my turning point in general, right, kind of not specific variables, it's going to be equal to this, right? So will my turning point, what will actually be true about it? If both these coefficients are positive, my turning point would be negative. I saw someone mouth there, right? Or I could think about how could I actually calculate this using stata? Well, I can use that display command. I know that it's going to be -1 times how do I get the dummy coefficient? I go underscore B, and then in brackets, I just use whatever variable name I want that coefficient of, which for us was whether or not the officer is male. Right? I then am going to divide that by the interaction terms coefficient. So I use this kind of underscore B syntax. Now, because I've created this variable, this is why I said it's kind of easier to do it this way. If I didn't, I could still like use like, male, driver male, hashtag years of service. You can do it that way. I just think it's easier if you create the variable itself. Now I just say, okay, I want that coefficient of the variable I created, which was the interaction term. And in fact, if you even wanted to, oops, if you don't have a bunch of regressions and you can keep track of it, maybe here I just call this my interaction term, right? And then I can just kind of call that coefficient my interaction term down here. So if I use that display command, what it should do is give me that turning point, which we said positive over a positive and a negative sign up front. The turning point for the marginal effect of being a male officer would be negative 15 years of service. Does this turning point make any sense in the context of this example? What's the lowest number of years of service you could have? 0. No, that doesn't make any sense. All right. So we always know the marginal effect here is actually going to be positive, and that the longer that the officer is on the job, that marginal effect of being male is getting higher and higher. So, I don't know, the story here would be something like, police officers on the job for 30 years, male officers become like old curmudgeons and just start handing out tickets to everybody, right? Because our Y variable, remember, was whether or not a ticket was issued. So these seem like small effects, but right, if this is a change in the probability I'm issued a ticket, that would actually be like for every additional 10 years of service, kind of increase in the probability that a male officer is going to issue a ticket if they're on the job 10 years longer, goes up by 0.03 or 3%. Okay. So we can kind of start to think about the size of these effects. If we have a dummy variable that's 1, 0, it's changes in the probability. Where there, change in the probability of 0.03 is like a 3% change. Okay. Now, just to kind of rehash some of these things we've talked about, if I have this dummy variable of whether or not a ticket was issued, what model can I not use here? So you might think, hear me starting to say, oh, probability of 0.03 as a percentage of 3%. Why don't I just use a logarithmic specification? Yeah, I can't use a logarithmic specification for a dummy variable because what's the natural log of 0? Undefined. So we can't use log or log linear models here. So we can still find the change in the probability of that 1, 0 Y variable. And we can kind of think about, okay, if it's a change in the probability, multiply by 100 to get a change in the percent. But we're not actually estimating a log linear relationship. We're estimating still a linear relationship, and we're really just identifying changes in that probability. Okay. So this would be how you can kind of use that display command, use the coefficients from the regression to kind of find this turning point. Okay. Any questions on that before we keep moving? Okay. Now, we did some of this last class, but what if instead I wanted the marginal effect of that continuous variable? So if I take a derivative of this function in respect to officers' years of service, all I'd be left with is, so I'm going to use that display command, the coefficient, on that continuous variable. And this is not a negative sign, this is a underscore there. And then what would also get added in? Well, here's where I'd actually have marginal effects vary for the group, right? Because what this would be is I would then add in, well, if I take a derivative in respect to the officer's years of service, I'd still be left with the coefficient on whether or not the officer was male, and right, times the dummy variable of, sorry, I said officer being male here. This is the, nice spell. Sorry, the coefficient on the interaction term between the officer being male and years of service, but then times that dummy variable, the officer being male. Right? So this is where if I've got my interaction term, when I take a derivative in respect to that continuous variable, years of service, I'm left with that dummy variable still multiplied by the value of the coefficient for the interaction term. So now here, I've got the marginal effect. I'll have two values that it's grabbing from the regression results for my coefficients, but what changes the marginal effect? Whether or not the officer is male. So I would actually need to make two predictions, right? So this would be my marginal effect. So I'm going to copy and paste this and think about, this is going to be the marginal effect for male officers. So this would be multiplied by a 1. But then if I wanted to know the marginal effect of years of service for female officers, well, now this officer male variable is equal to a 0. I really don't need to type this in because 0 times anything is 0, right? But if I run these two, what I can then see is the marginal effect of years of service is much smaller, well, not much smaller, but it is a little bit smaller for male officers than it is for female officers. Right? So I can start to identify, does the marginal effect of that continuous variable vary between the two groups? Now, once again, I can come up with these values. I'm being a little bit inappropriate here because what is the actual value of the coefficient on the interaction term? The p-value of 0.23, that value of the coefficient on the interaction term is actually, I can't say it's different from 0. All right, so I didn't really find a statistically significant effect that varies between males and female officers for years of service. Now, if I had, then that's how I would go about calculating what those marginal effects actually are. So before I forget, I am going to save this. So that we have all these edits. So if you weren't able to type as fast, right, I'll kind of have some of this in there. Okay, I'll put this on Canvas after class today. Okay. Any other questions over anything we've talked about up to this point? So one thing I would highly suggest when you're working on these models, especially in Stata for the next problem set, which I should have posted tomorrow, or I'll post it tomorrow. Focus on the one that's currently out there, but I don't want anyone to like get freaked out. They have to start working on the next one. I just want to get out as early as possible. Is I would write these regression equations out and have them looking at them in front of me. I would also, if we're not super comfortable and we're not taking crazy derivatives here, but I think one way to like keep track of what these marginal effects are is to look at the regression equation and remember that a marginal effect is simply taking a derivative, right? In respect to whatever you want to find the marginal effect for. Before this was really easy. Without interaction terms, that's essentially what a coefficient tells us. It tells us that when that x variable goes up by 1 unit, what is the predicted change in my y variable? That's literally a derivative, right? So those coefficients were, taking derivatives before, it was very easy, right? Now we just have multiple variables that have the same variable. So when we take a derivative, we're actually going to be taking a derivative in like multiple things. Right? So writing it out, I think, helps a lot of the time. Even the turning point, like when we get closer to the exam or you're thinking about the next quiz, don't try to memorize. I mean, you can, that it's negative coefficient on the dummy variable divided by the coefficient on the interaction term. I think if you write that out and take the derivative yourself and kind of do the algebra, you can always remind yourself, oh yeah, that's why the turning point is what it is. Now, once we get to the exam, I'll give you guys a formula sheet. So you don't have to do this like step by step and take a lot of time in the exam. But I think as you're working on these and the assignments, I would try to do that just to get really familiar with what these marginal effects are actually telling us and how do we identify what these turning points are. Okay. Any other questions here? Okay. So this is going to get a little harder now. So we don't have enough time to dive too deep today. But the next thing we're going to do is look at continuous variables times continuous variable interaction. Okay. So let's say I've got these two continuous variables and I want to include an interaction term between them. Okay. So here I can move this out of the way. There we go. If I think about the marginal effect of each continuous variable, I'll show you how we get these in a second. But notice the marginal effect of x1 depends on the value of x2. And the marginal effect of x2 will depend on the value of the other variable x1 that I interacted it with. So the marginal effect now of each variable is going to depend on the other variable it was interacted with. Okay, so why are the marginal effects looking like this? So once again, this is where I think just writing things out can be helpful. Okay, maybe I'll write this out with an example. I'll kind of keep it general here, and then I'll maybe use a variable so that we have something to kind of think about. All right. So my interaction term, once again, I could create this myself. It's just x1 times x2. I then throw that into my regression. So with continuous interactions, what's always going to increase? I'm adding in an additional variable, my r squared, right? Adding an additional variable, my r squared will always go up. Now, because I'm adding in a different variable, what gets penalized because of that? My adjusted r squared. So my r squared, when I include these interaction terms, dummy, continuous, always goes up. We don't know with certainty what's going to happen to our adjusted r squared. Okay? So if I'm doing this in general, if I think about what is that marginal effect of x1, well, it's really a derivative of this equation, y, in respect to x1 changing, right? Or in respect to x1. So I'd be left with what? My estimate on beta 1, well, the derivative of this in respect to x1 is nothing, right? Derivative here, I'd have the estimate on the interaction term, but I'm still left with the value of the other variable. And then if I wanted to know what's the marginal effect of this other continuous variable, x2, well, what am I left with there? The coefficient on the continuous variable, the second continuous variable, and then plus the interaction term times the value of the other variable. So that's where those marginal effects come from. Just taking a derivative of that original equation. So I could think about something like, this is what I'm dealing with right now. What's my performance on the final exam? And let's say I've got hours studied. I've got, well, here, make it to this class. I've got my previous exam score, and then I include an interaction of the two, all right? So if I was trying to predict all of your final exam scores based off of the number of hours you're studying and what you got in the midterm, well, if I had two individuals, a thought experiment would be, and they both got an 80 on the midterm, but one of them is studying more, right? Well, maybe the value of studying one more hour, it's different for someone who got an 80 on the midterm than it is for someone who got a 99, right? The same hours studied from someone who had 99 in the midterm, it's not going to be as effective at increasing their final exam performance as someone who maybe only got a 7, right? So depending on where you're at in the distribution of the midterm exam score, the effect of studying one more hour might be very different for you, right? So I've included an interaction between the two where I can look at the marginal effect here. So if I wanted to know what's the marginal effect of hours studied here, so the idea is if hours study goes up by 1 unit, my predicted final exam score would go up by whatever that coefficient is on hours studied. But then if hours study goes up by 1 unit here, it would also go up by beta 3, the estimate we had in the interaction term, but then multiplied by whatever your midterm exam score would be. Okay. So just to kind of put a thought experiment to this example, what do we likely hope the effect of 1 more hour studied on the final exam performance is? We hope that beta 1 is positive, right? Now, if I perform better on the midterm, what is the additional effect of an additional hour study? Well, I could kind of create probably two, I could imagine a intuition going either way here, right? If I perform better in the midterm, do I need to study more or less to grasp the material better than someone who did poor? Well, I must have already had a pretty good understanding. So if I put in the same additional hour, the marginal effect on my score is likely going to be higher than the marginal effect of 1 hour study for someone who got a 60, right? So I would likely expect if we had this data, it's likely that beta 3 is going to be positive, right? That people who perform better, if they were to put in the same 1 hour of additional study as someone who didn't perform as well, it's going to have a larger marginal effect, right? Now, maybe the people at the top, I don't know, they've already learned everything they can, so putting in another hour doesn't really improve their knowledge that much. So maybe this could be negative, and that's where we don't just want to guess, right? We want to actually run these regressions and look at what is that coefficient on the interaction. But you think about a lot of different examples where we don't have a dummy variable that we want to know the interaction between. We want to know the interaction between two continuous variables. Okay? And this is where it gets tricky because now our marginal effect varies with the value of the other variable that we interacted with. And it's not just simply a different marginal effect for the 0 and the 1 group. It's a different marginal effect for every single possible midterm exam score. Any questions, thoughts, concerns about this before we keep going here? Okay. Let me think here. I want to end things today. So just two things that are maybe stretching our minds a little bit. So the first thing I'll think about is what if I wanted to, and let's say, I'm going to not use general terms, I'll use this example. So let's say I wanted to know what is the marginal effect of hours studied, but I'm looking at different scores of the midterm exam. So let's say, I don't know, let's say our estimate for beta 1 was something like, these numbers might not make any sense. I'm just choosing some to have something here. And let's say this was equal to 0.2. Okay. Well, if I want to come up with a marginal effect here, if my midterm exam score was 0, we said the marginal effect is equal to beta 1 plus beta 3 times the individual's actual midterm exam score. So we would plug in these values, but then notice we could plot the marginal effect for every different possible value for the midterm exam score. So if the midterm exam score was 0, what's the marginal effect of an hour's study? Whatever beta 1 is, right? 0 times anything is 0. So we just kind of start out here at 0.5. Now, what if I'm looking at someone, once again, these values might not make sense, but just to kind of think about, if I have a 1 as my midterm exam score, maybe this is like in percentiles or something. Well, now what is the marginal effect? Beta 1 plus beta 3 times 1. So it would be up here at what? 0.7. And then if I had 2, the marginal effect is 0.5 plus 0.2 times 2. So I'd be up here at 0.9. Essentially, using these coefficients, I can plot out not the predicted value of my y variable. I could do that, but I could actually plot out what that marginal effect is and show how does it vary with that variable I interacted it with. Now, if we wanted, so any questions on that idea? Okay. So I've kind of shown you this a little bit in Stata. We'll probably dive into a little more deeply on Thursday. We had that like margins plot command I showed you a little bit. You could essentially calculate these marginal effects and plot them out in Stata. What would that also allow us to do? Something we've actually talked about. If I have my marginal effect depends on the other variable, what could I have here that we were talking about before with dummy continuous interaction terms? We could have a turning point, right? That potentially my marginal effect starts out as negative, and at some point it becomes positive. So we'll talk about on Thursday, how do we, with these continuous interactions, identify the turning point for those relationships? Any other questions before I throw one more kind of concept out at you? Definitely outside the scope of this class, but just interesting to kind of think about when we're talking about these interaction terms between continuous variables. So earlier, well, where's a better depiction that we were looking at? we said, oh, I know I had one. Maybe I didn't. Okay, well, we can use this one, right? So we said, when we're looking at marginal effects before, it allows us, here's it, I knew I had one. We can identify differences in the starting point and differences in kind of like the slope of that line of best fit. So with a dummy continuous interaction, this was kind of helpful to like be able to visualize this. It's not going to be as easy to visualize the line of best fit with two continuous variables because with a dummy variable, it shifted that line of best fit. If I have two continuous variables, instead of a linear plane, I've got one continuous variable that goes out this way, one that goes out this way. I've actually got a three-dimensional space. So my line of best fits, I can no longer visualize using 2 dimensions. I actually have this like three-dimensional kind of predicted Y value, which is why we can't plot out our predicted Y values, excuse me, but we can plot out the marginal effects. The marginal effects can still be depicted linearly. If I'm looking at just the actual Y value, I would actually now need to depict these lines of best fit as a three-dimensional shape. I'm not good at drawing 3 dimensions, right? It's very difficult to draw, right? We need some type of like, computer program to kind of help us create these nice visuals. So we wouldn't be able to do a similar thing with continuous interactions. But we can plot their marginal effects, not the actual predictions for Y, but the change that we would see exist in Y. Once again, a little bit outside the scope of this class, just kind of thinking about what we're doing kind of moving forward. Because I've seen people in some of these, you look at different like peer-reviewed published articles, you will sometimes see like people do like 4 continuous variable interactions because like we think that there's all these relationships between not just 2 but 3 or 4. I mean, there's no real way, for me at least, like some people like can visualize things in matrix form, like people that are really good with matrix algebra. That's just not my strong suit to be able to visualize that. But essentially, like you can include in as many continuous variable interactions as you want. You could have x1 times x2 times x3 times x4, right? For this class, and usually what you see, because once you start doing that, the interpretation of the coefficients doesn't really have a really good real world, interpretation. Usually you'll see people kind of just restrict that to kind of one continuous variable times one other continuous variable. So we'll get out of here, I guess, a little bit early today. I wanted to kind of make sure we introduce this idea of continuous interactions. We'll pick up on it on Thursday. I'm going to finish out that discussion. We'll jump back into Stata, look at how we do this in Stata, and then talk more about these turning points that exist with continuous variable interactions. So we should finish interaction terms this week. We'll then kind of start a new topic next week. Like I said, if you see that next problem set pop up, we haven't quite covered all the material, but I want to get it out there as early as possible. Make sure you're finishing up the one right now, problem set 4, that's due at the end of the day tomorrow. Okay? All right. Enjoy this nice weather, and I will see you guys on Thursday.